this video tutorial is prepared for internal consumptions only, and its main objective is to assist students of regression analysis course to understand and visualize the concepts that we have covered in lecture class. So this particular tutorial covers three most important topics. The first topic is about importing a comma delimited file or CSV file to SPSS. The second topic will be calculating or getting the sample correlation coefficient and testing hypothesis about population correlation and visualizing the relationship between two variables using scatter plot. And the third most important topic of this tutorial is fitting simple linear regression. So when it comes to the first topic, importing a file, so usually when you are working on secondary dataset, the dataset is not usually saved by the file extension that is well recognized by or opened by SPSS data editor window, which is .sav file extension. It would rather saved by spreadsheet-like software such as Excel, or saved as text file with different file extensions such as .txt, .dat, .csv. So among them, we are quite interested to import CSV files to SPSS because this kind of file extension is quite popular, and most of the online data repositories have preferred to put their data as a CSV file. So as a general rule, before you import any kind of secondary data, that's it, that is saved by different file extension other than .sav, we have to first open the dataset and we have to look at the nature or the structure of the dataset. So for this particular tutorial, I'm going to import a dataset called advertising, which is located on my desktop. So advertising CSV. If I double click on this dataset, the dataset will be opened automatically by Microsoft Excel, and that will hide some of the basic features of this dataset. So I would actually prefer to open this kind of dataset by using text editor like Notepad or Notepad++. So I have already opened this dataset, and the dataset looks like this. So as you can see, the first line of this dataset is reserved for variable names. We have a total of 5 variables: TV, radio, newspaper, sales, and including the first variable with no name. And the only separator between variables is comma, because it's a comma delimited file. And the first case is started at the second line of the file, as you can see it here. And the texts or the strings are qualified by double quotation. For instance, if you take TV, TV is now qualified by double quotation. So having noticed this thing about the nature of our dataset, let's open the SPSS data editor window and see the mechanism of opening or importing this kind of file. So SPSS has offered us 4 different possibilities of opening the open data dialog box. The first one is using this open icon or folder icon on the standard toolbar, or the second one is to use the Ctrl+O shortcut, which is equivalent with clicking on this folder. And the third option is to use file. We have to go to file, then open, after that data. And the last option is we have to use file as well, and file menu, and then read text data. So once the open dataset has come to the foreground, you have to see the files of type. So the files of type must contain the file extension that you want to import. So my file, the advertising.csv, is located on my desktop. I have to give complete path or the directory that the file is saved as on the desktop. Then I have to select the advertising.csv file. Then I have to click open. So the result will be the text import wizard with 6 different steps. We are expected to pass through 6 different steps. Actually 6 steps, each of them is very simple to figure out what's needed, and they are self-explanatory. So let's begin with step 1 of 6. The step 1 of 6 asks us one question. The question said that does your text file match a predefined format? Well, so far we didn't open this file before, and so we don't have any predefined format that's saved before, so I have to say no. And you have to see the data preview every time when you click on next, so there will be some kind of modification. So there is no predefined format. Then the first step is very simple. Just to move to step 2 of 6, we have to click on next. Then the second step, or step 2 of 6 of this wizard, is saying that how are your variables arranged. So before we have opened the original dataset and we have seen how the variables are arranged. So that's the main use of just opening the dataset before importing, because you know the true nature of your dataset. So we have two options here. The first option is delimiter. The second option is pixel width. Delimiter means variables are delimited by a specific character, comma or tab. So our file is a comma delimiter file. So the first option is our priority, or the only choice that we have. And the second question said that are variable names included at the top of your file? Well, as you can see from the preview area, the first line or the top of the file contains the variable names. We have 5 different variable names. So I have to say yes. When I said yes, you have to see the difference here. Now the first line of the file is gone or treated as a variable name by SPSS. So let's move to step 3 of 6 by clicking on next. Then step 3 of 6 asks us 3 different questions, and these 3 questions should be answered adequately. So the first question said that the first case of data begins on which line number. So the first line number is a variable name. So the first case of the data begins on line number 2. So I have to take the default value as it is. If the first case has started on the 3rd line or the 4th line or the 5th line, I have to make a modification here. And the second question is, how are your cases represented? Well, my case, the first case is represented by the 2nd line. So that means each line represents a case. Or we can choose the second option, which is a specific number of variables represent a case. So we have said that we have 5 variables. So a complete response for a particular case should be what? The response of 5 variables. So I have to say 5. So whenever you get a response for 5 observations, that is a complete response of a particular case. Or I have to say each line represents a case. So both of them are the same. As long as you have correctly specified the number of variables that a particular case can have. And the third question is, how many cases do you want to import? Well, if you have any kind of interest to import only a subset of your dataset, you have to choose the second and the third option. But for this particular tutorial, we need all the cases or the dataset to be imported. So I have to choose the first one. But if I need to import the first, let's say, 20, for instance, 20 cases, I have to choose the second option, and I have to place 20 in this white box. If I need to select randomly dash percentage of cases approximately, I have to prefer the third option, and I have to put the number of percentage that I want to import. So let me choose the first one. Then let me click on the next button to move to step 4 of 6. So step 4 of 6 is one of the important steps. Then it asks us 2 different questions. The first question is saying that which delimiters appear between variables. So the only delimiter that we have between variables is comma. So SPSS has successfully identified this delimiter. So it's not usually always correct. You have to identify the proper delimiter that appears between variables. It can be one delimiter, it can be more than one delimiter, so you have to correctly specify. And the next question is, what's the text qualifier? So as we have seen before, the text qualifier is with double quotation, so it has also successfully identified by SPSS. So I have nothing to change here at step 4 of 6. So let me click on next. Let me move on to step 4 of 5 of 6. So at step 5 of 6, I got one warning message. It said that invalid variable name for this application has been found and changed it. It's because the first variable doesn't have a name. So by the rule of naming a variable in SPSS, so there is no variable that we can declare without specifying its name, and the name should be unique, where it must not contain space between, and legal character should be removed. So I have to say okay. I have to make a modification on the variable name of the first variable. So the first variable is not v1, but instead it should be ID. So you can see the modification here. So at step 5 of 6, you have to rename variable names and make a modification on the variable type or data format. Then you have to click on next to move to the last step. So the last step asks us two questions. The first question said that would you like to save this file format for future use? This is the file that's needed at the first step of 6, if you remember. So we said that do you have any predefined file format for this file? And we said no, because we didn't open this file before and we didn't save any predefined format. So if you are interested to make a modification on the original dataset and import the modification to SPSS, you have to say yes and click on save as button, and you have to save the text predefined format or a file with EPF file extension. For me, I don't need to save any text file format, so I have to say no. And the second question is, would you like to paste the syntax? So if you need SPSS to give you the syntax equivalent of the step that we have passed through so far, you can click on yes. But if your priority is just to import the dataset, automatically when you click on finish, you have to say no and you have to click on finish.
So this is how the import dataset looks like. Here we have 5 different variables, as you can see here. So ID, TV, radio, newspaper, sales. So sales is the amount of money obtained by selling a product, and TV means the amount of money allocated for TV advertisement, and for radio advertisement, for newspaper advertisement. So this is all about importing text file. So the next topic would be calculating correlation coefficient and testing hypothesis about population correlation and plotting scatter plot. But before that, since we need to use this file for future use, we have to save it. So just to save, we have to click on the save icon on the standard toolbar. Then we have to specify the place where we want to save it. So I want to save it on desktop, and its name should be advertising. Well, so it's not a CSV file, so I have to remove this one. So the file extension should be SAV, so I have to click on save. That's it. So the file name is now advertising.sav. So hereafter I can easily open this file. So our next topic is about getting or calculating correlation coefficient and testing hypothesis about the population correlation and visualizing the relation between two variables using scatter plots. So for this particular purpose, I'm going to select two variables from the variables that I have here. So TV and sales. So TV means the amount of money allocated for TV advertisement, and sales means the amount of money that we get by selling a product. So to get the correlation coefficient, let's go to the Analyze menu, go down to Correlate, and then click on Bivariate. So the Bivariate correlation dialog box come to the foreground. So I have to select two variables from the left side of the dialog box, and
put it to the variables box here to activate the algebra type, because correlation coefficient is calculated based on two variables. So we need to have at least two variables on this variables box. So let me select TV and sales. So when you see the correlation coefficient, these variables, SPSS can offer us to three different techniques to calculate the correlation coefficient. The first one is the formula proposed by Carl Pearson, and the second one is Candelas-Taubes, and the third one is Spearman. So in class, we have seen the Pearson correlation coefficient, or the formula that is proposed by the well-known statistician called Carl Pearson. So I have to take the default as it is. So when it comes to the hypothesis testing, SPSS is offering us two different alternatives for the alternative hypothesis. Its main purpose is just to test whether rho is equal to 0 or not. So that means the null hypothesis is going to be the population correlation coefficient is equal to 0, and the alternative may be the population correlation coefficient is different from 0, or it can be greater than or less than 0 if we are quite interested about the one-tailed hypothesis testing. But for the time being, we are interested about the two-tailed hypothesis testing, so the alternative hypothesis is not expected to show any direction. So the population correlation coefficient rho is different from 0. So by formulating this kind of hypothesis, we are saying that the null hypothesis is interpreted as the two variables, in our case, the TV and sales, do not have any linear shape. And the alternative is saying that TV and sales have a significant linear shape. So let's go back to the dialog box, and we have to choose the default two-tailed hypothesis testing, and we have to also take the we have to let SPSS to inform us about the status of our hypothesis, whether it's significant or not. So let SPSS give us the flag of significant correlations. So after that, we have to press OK. Then the result published on the output viewer. So it's a kind of table, a matrix. It has a lot of information in it. So the first information is about the sample correlation coefficient between TV and sales, because the correlation coefficient between TV and itself is expected to be 1, and the correlation coefficient between sales and itself is 1. So it's not our interest. Our interest is just to see the correlation coefficient between TV and sales. So the correlation coefficient is 0.782, which is greater than 0 and close to 1. And the other information is about the hypothesis testing of the population correlation coefficient. So this is the p-value. So we have to compare p-value with alpha value. So alpha value can be determined by us, and the default value is 0.05. So when we compare the p-value with alpha, p-value is smaller, so we have to reject the null hypothesis. So the null hypothesis was saying that the TV and sales do not have linearity between them. So we have to reject this hypothesis and conclude in favor of the alternative one. The alternative is saying that TV and sales have a significant linearity. So this result can be considered as a green light to fit a simple linear equation. So there is a possibility of writing sales as a linear function of TV, because sales is the dependent and TV is the independent. So this is all about the bivariate correlation coefficient and hypothesis testing. And the third information is the number of observations considered to calculate the Pearson correlation coefficient and to conduct hypothesis testing. So we have 200 observations or cases in our dataset. So let's go to the scatter plot, because scatter plot and correlation coefficient can be used to see the type of relationship that the two variables can possibly have. So go to graph and the Gaussian dialogues. After that, scatter plot. So here we have plenty of options. So I have to prefer the simple scatter, and I have to click on the define. So we have said that sales is the dependent variable and TV is independent variable. So I have to move sales to the y-axis and TV to the x-axis. So cells to the y-axis, TV to the x-axis. So this is all about the scatter plot, and the result will be published on the output window. So this is how the scatter plot between TV and cells looks like. It's a kind of upward linear relationship, and that's why the correlation coefficient becomes positive 0.782. So there's a linear trend between TV and cells. So just to make a modification on this graph, let's double click on it. Then the chart editor window comes to the foreground, and chart editor window is used to edit the graph in the way that we like. So whenever you need any kind of modification, you have to select the area that you want the modification to be applied. So the first step is just to change the background color. It's gray, but I want to make it white. So I have to select the background. The background is selected. So the property dialog box is come to the foreground. So I have to choose the white color and click on apply. Then the change is happened on the graph. So let's say I want to change the marker. So I have to select the marker, and the marker is expected to be filled by some color, let's say red. So I have to click on the field, then red color, after that apply. So the next step is just fitting a linear regression on this scatter plot. I want to know how the feature line looks like on this scatter plot. So we have to go to this add feature line at total icon on the standard toolbar of chart editor. So let's click on it. So here it is. So this is the line, the featured regression line. So the featured regression line has an equation of that is y is equal to 7.03 plus 0.05 times x means TV, y means cells. So its R squared is 0.612. So let me remove this level because I don't want it to be there. So I have to select it and go to the reference line from the property. Then I have to select the attached label to line. So I have to say apply. So now the label has gone, and I want to make a modification on this level. So instead of just putting outside of the graph, why not I put it inside the graph? So let me drag it to the place where I want this label to be placed. So here it is. So after that, once you are done with editing your data, your graph, you have to close the chart editor window, and the modification appears on the output window. So we need to export this graph to other graph file extension like PNG or JPG. So to do that, we have to right click on the graph that we want to export and click on export. Then the export output dialog box comes to the foreground. So from the object to export, I want to export only the selected file, the selected graph. And from the document, you have to make sure that none or bracket graphics only is selected, because here we have different options, but I want the last one. And from the graphics part, I have to select what kind of image I want to export. So the two most popular graph extensions are JPG and PNG. I prefer PNG. So I have to tell SPSS where this file is exported. So it should be on the desktop with scatter, with file name scatter, and I have to say save. Now this is the complete path of the file that I want to export. So I have to say okay. So if the file is too big, it will take some time to export the file, but if the file that you want to export is small like this one, it's just a matter of seconds to export to the file, to the desired directory. So this is the file. So this is the scatter.png file. So this is an image file. You can open it and copy it and paste it somewhere else. So this is all about the second topic of this session. The next topic is fitting simple linear regression. So in the previous topic we have seen how we can calculate correlation coefficient and testing hypothesis about the population correlation and examining the relationship between TB and sales using scatter plots. So all the results that we have done so far have suggested that there is a possibility of fitting a linear regression. So sales is going to be our dependent variable and TB is our independent variable. So to fit a simple linear regression, we have to go to analyze and regression, go down to regression and click on linear. So this is the linear regression dialog box. It has two most important boxes here, dependent and independent or independent variables. So we have to select sales and put it to the dependent box, and we have to select TB and put it to the independent box. So as you can see, the method is entered. That means all the independent variables are expected to be entered at the final model. There is no variable selection at all. Well, so at this point, we don't need any kind of variable selection method. So we don't, change the default method of fitting linear regression. For the first time, let's say that this is sales and this is PV and it's a simple linear regression. Sales equal with beta naught plus beta 1 TB plus the random disturbance term epsilon. Now, when you press OK, this is the result, which is published on the output view window. So the first table is given the information of the model building strategy. It is an enter method, and the variable entered is TB, and there is no variable that we removed, and the method is called enter. There is no variable selection method. The default is enter. And when it comes to the model summary, here we have the R. R means the correlation coefficient between the dependent variable and the independent variable, TB and sales. It is 0.782. So for simple linear regression, R square means the square of this R. So 0.782 square means 0.612. So far we didn't cover anything about the registrar square, so I will leave it. And the R square, the result suggests that about 61.2% of the variation of sales can be explained by the TB. So one independent variable is able to explain 61.2% of variation of the dependent variable or amount of sales. So when you go down, you get the regression ANOVA table. We have two sources of variation, regression and residual. And here are the sum squares, sum square regression and sum square residual and sum square total. And degree of freedom for regression and degree of freedom for residual and degree of freedom for the total. And mean square means sum square divided by degree of freedom. So since the degree of freedom for regression is 1 and sum square regression and mean square regression are the same. And the mean square error or residual is sum square error divided by the degree of freedom, then it's 10.619. And the test statistic F is the ratio of mean square regression to mean square error. So 3,314.618 divided by 10.619 will give us 312.145. So ANOVA is testing the overall goodness of the model. So above the ANOVA table, R square is greater than 0.5, about 61 or 62% of the variation of sales is explained by TB, so the model is expected to be good. So the same conclusion can be drawn by using the ANOVA table. So here is the p-value. The p-value is less than alpha. Alpha is 0.05. If the p-value is less than alpha, we have to reject the null hypothesis. So the null hypothesis of the ANOVA table is say that the model that we are fitting is not capturing the data. Or, in other words, it's just to mean that the model is useless for prediction. or the model is not capturing the necessary patterns hidden in the dataset. So we have rejected this hypothesis and decided forward the alternative one. The alternative hypothesis is saying that the model is capturing the data very well. So the goodness of fit test is significant, and so does the R square. R square is also indicating that the model is good because by using only one independent variable, we are able to explain, more than half of the variation of sales. And you have to imagine how the model will be developed if we add another independent variable. So the last table is coefficients. Constant means here the beta naught hat. TV means beta 1 hat because beta 1 hat is the coefficient associated with the independent variable TV. So this is unstandardized coefficient, or the beta value is 7.033, and beta 1 hat is 0.048. So that means our model, let's say y hat equal with 7.033 plus 0.048 times TB. So this is the fitted linear regression model. So this is the intercept, and this is the slope. So the slope can be interpreted as if we increase the amount of money that's allocated for TV advertisement by 1 unit, and the amount of sales will increase by 0.048 amount. So this is the slope, and the intercept doesn't have any kind of practical meaning here because the range of TV doesn't contain the value 0. And this is the standard error, or the standard deviation of beta naught hats and standard deviation of beta 1 hats. So we didn't cover anything about the standardized coefficient, so let's left this part. And this T is the value of the base test statistic T, and this one is a p-value. So here the first p-value is 0.00. The null hypothesis for the constant is saying that the inclusion of the intercept is unnecessary in our model. So that means the model is can be specified as beta 1 times TV plus the random disturbance term. So because the intercept is 0. So the alternative is beta naught is different from 0. So since p-value is less than alpha, we are rejecting the null hypothesis. So we are deciding in favor of the alternative one, and the conclusion is that the inclusion of the intercept into our model is necessary. And the second coefficient, the second hypothesis testing is say that beta 1 is equal to 0. So that means the variable that's associated with beta 1 is useless, or is not able to explain the variation of the independent variable sales. So the alternative is saying that the inclusion of the independent variable TB to the model is necessary. So if the null hypothesis is true, it's just to mean that TB and sales do not have any kind of linear relationship. So that means the correlation coefficient should be 0, or the hypothesis about the population correlation coefficient should not be rejected. So since the population correlation hypothesis testing is shown as significant, and so does the hypothesis testing for the intercept, because they are directly related. So testing H0 beta 1 equal to 0 is equal with testing rho, the correlation coefficient between TB and sales goes to 0, are the same. So in both cases, the test is significant. That means we are rejecting the null hypothesis and deciding in favor of the alternative one. So the inclusion of TB in our model is good. So this is all about the coefficients and the corresponding hypothesis testing. So let's go back again to the linear regression dialog box and try to construct confidence interval for the coefficients, the beta naught hat and beta 1 hat, or constant and TV. So the dependent variable sales, the independent is TV, so we have to select statistics. Statistics button gives us a number of results, but I need to know the confidence interval. So from the regression coefficient box, we have to select coefficient confidence interval, and the level is 95% by default. If I take the default value, that means I'm going to construct a 95% confidence interval for beta naught and beta 1, but let me change this value. I have to make it 99%. So I want to construct a 99% confidence interval. That means our alpha is 0.01 or 1%. So let me press on continue button, and let's say okay. So the only difference comes here on the coefficients table. So this is a 99% confidence interval. So the lower bound for the beta naught is 5.042 and the upper bound is 8.223. So we are 99% confident that the unknown or the two population parameter beta naught is lying between this interval. So confidence interval and two-sided hypothesis testing have a direct relation. If the hypothesized value is inside the constructed confidence interval, that means we don't have enough evidence to reject the null hypothesis and decide in the favor of the alternative one. So when it comes to the hypothesis testing of coefficients, the hypothesized value is 0. So is 0 between these two intervals? No, it's not. It's not between 5.84 and 8.22. So we have to reject the null hypothesis. So the confidence interval is suggesting that the hypothesis should be rejected, and the p-value is suggesting the same thing. And when it comes to the 99% confidence interval for beta 1, as 0.041 and 0.055. So we are 99% confident that the unknown two population parameter beta 1 lies between this interval, and the hypothesized value 0 is not part of this interval, so we have to reject the null hypothesis as we did by using the p-value. So this is all about the constructing confidence interval for the model parameters. And now let's go back to the regression, the linear regression dialog box, and we need to calculate the predicted value for sales, the value of the sales that's predicted by the linear model. So I have to go to the save button, and from the predicted value box I have to select unstandardized value, unstandardized predicted value. And from the prediction interval we have two different level of types of confidence interval or prediction interval for the response y naught for a given value of x equals to x naught. So the first one is the mean response, when the value of x naught is inside the range of x, or in our case TV, or we need to construct a prediction interval for future observation when that TV or x equals to x naught is outside the range of TV. That's used to fit the linear regression model. So for the mean response confidence interval, I have to click on the mean, and I have to adjust the confidence level. It can be 99, 95, or anything between 0 and 100. So let me take the default 95% confidence interval, and let me save the residual. So residual, in a sense, the actual value minus the predicted value. So I want to click on it, and I have to click on continue. Now I will have 1, 2, 3, 4 different variables from the active dataset, and I will explain each of them later on. So let's press continue, then okay. So let's go back to the data editor window. From the data editor window, previously we have like 5 variables from ID up to sales. Now we have additional 1, 2, 3, 4 variables. So this PRE_1 is the unstandardized predicted value, and RES_1 is unstandardized residual, and this LMSE1 means 95% confidence interval for sales mean, and this is the upper limit of a 95% confidence interval for the mean response of sales. So this is the confidence interval, these two, the lower and the upper, the upper and the lower, and this is the residual. So residual means the sales, the actual value minus the predicted value. So 22.1 minus 17.97077 must give 4.12923. Let me check this one using calculator. So the actual value of sale is 22.1 minus the predicted value 17.97077. So the residual is 4.12923. It's perfect. So this is all about fitting a linear regression using SPSS. So in the previous section, we have seen how we can plot or draw a scatter plot for two variables, sales and TB. And let me modify this scatter plots for additional task. So we have said that the confidence interval for the mean response of Y or sales is minimum when TB equal with the average amount of money allocated for TV advertisement. And the confidence interval is wider and wider when the value of TV is far from the average value of TV advertisement money. So let me select the fitted line. Here it is. So I want to construct confidence interval from the property. So I have selected the fitted line, and this property dialog box has come to the foreground. So I want to construct a 95% confidence interval for the mean response of sales. So I don't want to attach level to line. So I have to go to click on apply, and you can see the change here. You see, as you can see, so at the point where TV equal with the average amount of money allocated for TV advertisement, the confidence interval is minimal. The difference between the upper and the lower bound is small. And when it goes up, when the difference between the actual money allocated for TV advertisement and the average amount of money allocated for TV advertisement is larger, then you'll see a wider confidence interval. So this is all about this video tutorial. If you have any kind of question, you are welcome to ask me in person. I hope you have enjoyed this video tutorial. I feel sorry for the quality of the voice, and thank you for watching.